Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I want to welcome you to our monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of renewable energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. I also serve in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and scale. ESIG leads one of the 5 pillars which deals with the research agenda for the system operators. More information on the GPST can be found at www.globalpst.org. We're quite busy going into the new year, having just finished up our spring technical workshop and preparing for our forecasting and markets workshop in June. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, and Twitter. Okay, just a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we've moved to the Slido platform, and we're asking you to ask your questions through Slido at slido.com. You will not be able to ask your questions through WebEx. So go to slido.com and enter ESIG20 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today's topic will be on the role of grid enhancing technologies in unlocking interconnection queues. This topic has been receiving a lot of attention lately, and after the presentation, I think you'll know why. The webinar will feature Jay Caspary of Grid Strategies, previously with SPP, and Bruce Tsuchida of the Brattle Group. Both Jay and Bruce are familiar faces to many of you and have been working in the area of transmission for quite a while. They're well-known figures nationally and will cover a recent study they did, which has been getting a lot of attention around the country. It covers the potential application of the grid-enhancing technologies of dynamic line rating, topology control, and power flow control on the SPP system. I feel very fortunate to have Jay and Bruce here with us today. For some reason, I haven't been checking on common connections on LinkedIn lately, as I have been in the habit of doing. So I went on last night to see how many common connections we have, and I found out that between Jay and Bruce, we have 500 mutual connections. I guess when you work together for a long time, you run into the same people. Anyway, Jay served on our board for a number of years, and Bruce has also been an active participant in ESIG for quite a while. They're both good friends and good friends of ESIG, and it's a real pleasure having them here with us today. The webinar will look at the potential application of grid-enhancing technologies on the SPP system and the critical role they can play in greatly expanding the interconnection of renewable energy capacity already in the SPP queue over the next 5 years. Just a short reminder once again to use Slido at slido.com with the event code of ESIG20 to ask your questions. Okay, without any further ado, let's go ahead and get started. And Jay, I'll now turn it over to you.
Thank you, Charlie. Can you hear me okay?
Yeah, we hear you good.
Great. So thanks for giving Bruce and I the opportunity to share this slide deck is posted out on the Watt Coalition page. And on the front of the first slide, you'll see a link to the actual posting that is available in terms of the full report as well as the release. We had a very large launch event back in February, late February. It's hard to believe it's been almost 8 weeks. that actually had Chair Castor from Florida giving a keynote and me giving a very high level overview of the study, and then a panel which involved Jeannie Irwin with Smart Wires being a moderator with 4 really good panelists, including Radhika Donaldson with EDF Renewables, as well as Al Tamimi with Sunflower Electric, and Rudy Winters with National Group and others. I think you'll find it very interesting. I'd encourage you to check out the recording as well as the full report that's available. So today, Bruce and I are going to spend some time. I'd encourage you to use Slido, ask questions, and we're going to go through a case study of how we could use grid enhancing technologies, looking at a subset of SPP, the states of Oklahoma and Kansas, based on real world models and planned approved project additions as well as resource changes to integrate additional renewables that are waiting in the queue right now. Projects that have signed IAs but have not committed to integrate it into the system for whatever reason. But this shows how we can use grid enhancing technologies to facilitate getting more renewables onto the grid. We know we can also use grid enhancing technologies to manage congestion today. I mean, grid enhancing technologies are proven throughout the world. They're being used quite a bit more in Europe than they are in the US for lots of reasons. And hopefully this report will help the dialogue and understanding about the potential applications and merits of grid enhancing technologies in a case study for Southwest Power Pool. Let's go forward to the second slide, which is a cover of the deck that we've had. Before we do that, I'm a really big fan of ESIG. I'd encourage you to stay engaged with ESIG, and you won't be disappointed, and you're going to get a lot of benefits from the relationships and just the contacts you get at these events. So thanks, Charlie, for giving us an opportunity to talk about this report. Bruce Tsuchida, who's going to talk about the details as well as the results. I'll kind of tee this off. Bruce was the lead in terms of the analysis. The study was done by the Watt Coalition. Talk a little bit about that, as well as the technologies. They've been called grid enhancing technologies. Some places they call them advanced transmission technologies. They're basically non-wire solutions that are looking at ways to get the most out of the existing and planned transmission system. We'll talk about this in the context of SPP and these 2025 models that we did, and a lot of reliability analysis, a lot of power flows that Bruce and his staff did to actually try to determine a new base case out in 2025, as well as what benefits we could see from deploying these technologies in aggregate on the SPP system to help integrate renewables. SPP has a lot of wind, and we've all seen the price contour maps that show the congestion on the system. You'll see it today. It's up in the Dakotas, the dark purples in western North Dakota, and then you see the bright yellow and orange and red prices just east of there on the other side of the pricing constraints and the transmission congestion that actually exists on the system today. SPP is going to get more wind too, and they've got challenges today with integrating renewables. I was looking at the wind profiles for next week, and it looks like the first time on the mornings of the 26th and the 27th, SPP wind forecasts actually exceed the net system load requirements, up over 23 gigawatts of wind and slightly less amount of that of load. So I'm sure SPP is going to see tremendous amounts of curtailments over the weekend and into next week. And these technologies could be used to help manage that today. But the purpose of this study was to look and see how many additional megawatts of wind in the queue could we integrate by deploying grid enhancing technologies. Let's go forward. We have a slide that has a typical disclaimer. I do not plan on reading this. I do want to recognize the Watt Coalition members and the sponsors of the study. The people that actually paid for this study and helped us fund it, as well as the significant support and technical analysis and advice we got from the technology vendors at Ampassion, at Lindsay Manufacturing, Line Vision, as well as Himdall Power, who are all four dynamic line rating companies who are part of the Watt Coalition. In addition, we have WindSim, who helps with wind forecasting. And we also have New Grid, who helps with topology optimization, which is a software solution, as well as Smart Wires, which is advanced power flow control devices that are being deployed significantly in Europe as we speak and being tested in the US. Those are the members of the Watt Coalition. The people that sponsored it include GridLab. I'd encourage you to check out gridlab.org. They do some really good work in terms of analytics, testimony, ERPs, analysis, recommendations on how to integrate more renewables into the system, as well as some SPP members, including EDF Renewables North America, NextEra, and Duke, who actually sponsored the study. I want to thank them. Without them, we wouldn't have done this. But we're going to go through the slides now and talk a little bit about why we did the study. So the issue at hand, we've seen significant decarbonization goals recently. It's not just the Biden climate plan and the desire to get to zero emissions carbon in 2035 on the power grid. That's significant. It's going to take a lot of changes to the system and probably lots of transmission if we're going to do it efficiently and effectively and reliably. But these goals are significant. And it's not just coming from utilities or states, it's from corporations or institutions, as well as, cities and municipalities, significantly being affected by customers, end use customers and big retail establishments who have very aggressive carbon reduction goals. The map on the bottom actually shows the service territories of utilities that have announced significant carbon reduction goals. The mass majority of the eastern U.S. and splattered throughout the central and western U.S. have major goals to reduce carbon. So let's go forward and talk a little bit about some roadblocks, I guess, to integrating more renewables. We talked about SPP. Wind was the leading resource for energy sales in SPP in 2020. It's only going to continue to grow. SPP spent a lot of money and time to expand its footprint, to consolidate BAs, to add transmission, to change reliability protocols, to be able to, in market structures, to be able to integrate significant amounts of wind. I can't imagine they're up over 82% wind penetration levels. Who would ever thought we'd be there? 10 years ago, we couldn't even get a 30% wind model to solve. But transmission has been a major enabling device to accommodate all of that. There's also significant interest in more renewables getting onto the system. Just look at the generation interconnection queues. And the cost of these renewables continue to decline. So there's going to be more and more pressure as we get to cleaner and cheaper energy on this grid. So why do we do this? How can grid enhancing technologies help us integrate more renewables? And that was the whole purpose of this study. Let's see if we can actually use real models with reasonable updates and conservative assumptions to see how much benefit we could get from grid enhancing technologies on the planned transmission system and resource mix that SPP was projecting in 2025. Let's go forward and talk a little bit about the study overview. Let's talk about the technologies, I guess. But grid enhancing technologies, you've probably all heard of them. There's been a lot of pilots. There's been a lot of case studies and papers. But grid enhancing technologies not only help operations, but they can help planning. This focus here is primarily in operations. But we see grid enhancing technologies as a complement to new transmission and definitely a bridge to fill the timing gap between the permanent transmission expansion solutions that we expect we're going to need to get to a clean, carbon-free grid in 2035, but also to help us do it more efficiently and deploy these technologies throughout the system and move them around physically, actually, as the congestion on the system does evolve. We're going to focus on three major types of grid enhancing technologies in this assessment. The first is advanced power flow controllers. These devices actually inject voltage to change the apparent impedance of transmission lines. They either add impedance, which causes less flow on the line as congestion, or they increase impedance or decrease impedance and cause additional flow to come online. And they do this to push and pull power on underutilized assets or overloaded assets as needed. The second type of grid enhancing technology is dynamic line ratings. That's been getting a lot of attention at FERC with the NOPR that's out there, and the managing line ratings and the push for ambient adjusted ratings being mandatory in organized markets, as well as the ability to use DLRs where it's appropriate. And dynamic line ratings, you know, we always assume certain parameters about weather conditions in our static planning models and assumptions for facility ratings, particularly line ratings. And wind has a major effect on that, as does temperature and the solar absorptivity and things like that. But the important thing, I think, is wind. And what we know from these models is because we're actually going to use actual models and we know exact conditions, so we can actually calculate what the DLR impact should be on the conductor for the limiting lines in these simulations. The last type of grid enhancing technology we want to talk about and use in the course of this investigation is topology optimization. This is a software solution that helps you to identify, much like Waze does in terms of giving you a preferred route for managing traffic congestion on your commute home or travels in the summer and winter. You can use software that helps you identify how you might change your route or reconfigure the system, the topology of network, to relieve loading on overflowed lines, over congested lines, and take advantage of latent capacity of additional lines that may not be being used, but could be made available if the apparent impedance would change and the system reconfiguration were deployed. So that's kind of an overview of the study. I want to start going through the study approach, and then I'd like to hand this off to Bruce and let him go through the modeling as well as the results, and I look forward to your questions. So I want to go through, I can do this slide, and then I'm going to hand it over to Bruce, okay? One of the reasons that we actually looked at Kansas and Oklahoma, there's several, but if you look at the planning studies that have been done in SPP the last few years, all these studies have identified significant congestion and constraints on the power system between Southeast Kansas and Southwest Missouri, as well as in East Central Oklahoma. So we know there's challenges there, and there's a need to expand the system in the next few years to address those constraints. So that's one of the reasons of why we wanted to look at this. The other reason is there's an excess of 9 gigawatts of potential proposed new wind farms and solar projects in Oklahoma and Kansas that have gone through the study process and actually have signed interconnection agreements but haven't committed to moving forward. What we wanted to do in this analysis to establish a new baseline in 2025 based on expected conditions to identify first how many of that 9 gigawatts of new potential renewable resources with signed IAs in Kansas and Oklahoma could be connected to the system without overloading lines or having significant voltage issues in terms of power flow analysis. And then we wanted to look at what would happen should we deploy dynamic line ratings and then topology optimization and then advanced power flow control devices on top of that, and how many more additional megawatts of renewables could be integrated onto the system. So we're going to look at this not only in terms of just the additional megawatts, but we want to look at the energy that we'd get from these new renewable interconnections, as well as the economic benefits of doing that. This energy is going to displace additional thermal resources probably on the system, and what's that worth? How much are the investments? How many jobs will be created, as well as tax revenues and land lease payments and things like that. as well as the environmental benefits. So with that, I think I'd like to hand it over to Bruce and let him go through some of the more details of the study. We look forward to your questions and appreciate your attention. Thank you. Bruce, are you ready?
Thank you, Jay. Muted. I will continue off with where Jay left, but there's one picture that I want to show you before we go into the results. This is slide 25 or 24 rather, for you folks on the phone. It shows a diagram of from SPP back from November 18th, 2020. The red line and the green line are and midterm wind forecast. So you can see that the wind forecast has been persistent, but the orange line that goes below is the actual wind. And we blew it up in the bottom, and the area of the difference is the curtailment. Given that the long-term and the midterm and the short-term wind forecast has been persistent, and the load forecast that you see on the top is also persistent, this suggests that the curtailment was actually caused by transmission congestion. And the GETS technologies that we're talking about here can potentially help in those situations where it's not because of minimum generation issues, but more of transmission congestion that you did not anticipate. So going back to the study, what we did was we tried to model the three respective technologies in the order of dynamic line rating first, followed by topology optimization, and then by advanced power flow control, and see how much additional renewables we could integrate. This order is important because we're starting with dynamic, going to topology optimization, and then followed by advanced power flow control. So naturally, dynamic line rating will be benefits, followed by topology optimization, and there's probably not much left for advanced power flow control. So please do not try to figure out which technology is the best, because that was not the purpose of the study. All we tried to do was, with the combination of these three technologies, what would be the benefits that they combined can provide. To start with that, we looked at 24 different representative snapshots from SPP, taken between summer of 2019 through summer of 2020 to represent a full year. I am going to jump to slide 34 that shows the diagram that you see on the right-hand side that looks like a lot of blue lines and red lines with a black line going into the middle. This diagram is actually how we split the year into 25 different segments. The area between the line is a bin. And how we did that was we tried to split the year into 25 different segments with equal amounts of wind curtailment in SPP, which is roughly 56 or 57,000 megawatt hours. And then, so every area in between the red lines will have equal amounts of renewable curtailments. And the further right to the right of the chart you go to, the area or the distance between the red line becomes very, very narrower because you see more and more curtailments. The table in the middle you see on slide 33 presented here shows the amount of curtailment, which is constant in absolute terms for each bin, the amount of wind production, which goes up because curtailment is reduced, and the number of hours that each of these 25 bins represent. What we did was we analyzed the top 24 bins because the last bin, or the most wide area that you see with high net load, the curtailment was really, really small. And so we analyzed the first 24 bins. And the table on the right shows the different snapshots that we took for each of the bin. SPP provides snapshots for early morning at 5 a.m., midday at 11 a.m., late afternoon at 5 p.m., and late night at 11 p.m. For each of these 24 bins, we selected a snapshot that roughly represents the curtailment level and the load level that we tried to represent through the bins. Now, because we had the actual date and the time, we were able to model the dynamic line rating using exact weather conditions of each of these representative snapshots. So that's what we did to find the amount of renewables that can be integrated. One more additional thing about the model is that we tried to model 2025, and the model 2025 reflected all the new transmission upgrades that have been approved, the renewable projects, the 9 gigawatts or so from the generation interconnection queue that has interconnection agreements, adjusted the generation for announced retirements and new. We adjusted for load change, especially the Lubbock load in Texas is going to migrate gone by 2025. Replicate what would happen in 2025. So the first thing that we had to do was figure out how much thermal generation could go down to accommodate the wind. We made rough assumptions looking at the power flow case, saying any power plant that's above 100 megawatts can only go down to 30% of their rated capacity. If it's a gas turbine generator, it could probably shut down if needed. If it's a gas combined cycle, it may shut down during the nighttime snapshots, but not during the daytime snapshots. Nuclear plants will not move their change their outputs regardless of how much wind there is. And to be conservative, we decided to leave the import-exports from SPP to neighboring systems constant. So there were no additional exports or reduced imports associated with increasing wind and solar within SPP. What we did was we took the 9 gigawatts of all the new generators, the renewable generators that were in the queue. We plugged it into the power flow case for every of the 24 snapshots, ran the security constraint optimal power flow case to make no reliability violations, and then took out the ones that had high renewable. And then we added back the remaining bunch, SCOPF again, figured out which ones would have high curtailments, and took it out, and repeated that until all the power plant, all the projects that were left in the model resulted in a 5% or lower curtailment for the entire year. Because we're splitting the year into 24 different snapshots, with some of the snapshots may have shown curtailments that were higher than 5, but because every snapshot had a weight such as 3% to 5% to 20% of the year, if the total curtailment within the year was less than 5%, we left the project in assuming that those were viable. This 5% comes from our discussion with various developers saying and we asked the question, if you were developing a project and you had some prediction or forecast on curtailment, what would be the rough ballpark of where you would assume the project to be viable or not? And the 5% was pulled out from discussion with various developers. So at the very end, we looked at the GIQ. There were 9 gigawatts of renewable resources that had interconnection agreements. We analyzed the combination of those and narrowed it down on a project-by-project basis until the projects that were left all had a 5% curtailment or lower level of curtailments to figure out how much we can integrate the additional renewables. We did the same analysis for 2 scenarios. One is for the base case without the grid enhancing technologies, and the second one with the grid enhancing technologies. So here are the results. The table at the upper right-hand side shows the potential 9.4 gigawatts of renewable resource projects that were in the interconnection queue with the interconnection agreement executed. These guys can go into construction at any given time if they would want to. Obviously, because it's SPP, a huge portion of that is wind. Within the base case, without the grid enhancing technologies, we found that the current system, or the system as of 2025, can integrate about 2.6 gigawatts of renewables, with a huge portion of that being wind. Now, once we add the GETS technology, that doubles to close to 5.3 gigawatts. And the delta of 2.7 gigawatts is enabled by GETS is roughly 1.5 times the amount of wind SPP integrated in 2019 alone. So you can see how impactful that is. In other ways of saying it, GETS can help integrate 2.7 gigawatts of additional renewables just without adding anything more to the transmission. The benefits did not only result in how much additional renewables you can add, it also reduced the curtailment of existing renewables, obviously, because you're enhancing the transmission grid to be utilized even better. So with the reduction in existing wind curtailment, plus the new wind and additional new solar, the total amount of energy that we could enable through GETS, roughly 2.7 gigawatts of new renewables, added up to about 8.8 gigawatt hours. Now, if you assume 8.8 gigawatt hours replaces energy that's at about $20 per megawatt hour, which is lower than the SPP LMP of the last year, that adds up to about $175 million, as we see in the very bottom diagram. The installation cost is only about $90 million, with the annual O&M estimated to be about $10 million. So for $90 million plus $10 million a year, you can save $175 million. Other benefits include that you reduce carbon emission by roughly 3 million tons a year. There's substantial long-term and short-term jobs that the GETS can enable. And there's also other local benefits such as land lease and tax revenues to the state by year associated with the increased renewables. So slide 11 summarizes how we came up with the calculation. There's more details of the calculation in the actual deck, which is quite large. But the takeaway is that, yes, there's a significant amount of production cost savings. So the payback for the grid enhancing technology is only about half a year. Even if we conservatively assume it's $20 per megawatt hour, it adds up to quite a big number. The carbon reduction is over 3 million tons a year, and that's only assuming that all the generation is replacing a natural gas fired combined cycle plant, which is one of the least emitting resources out there. If you're replacing less efficient resources with higher heat rates and higher emission rates, the amount of carbon that's going to be reduced is probably a lot higher than what that is. Now, if you take the results and assume how that will grow nationwide, we found that the combined generation from Kansas and Oklahoma was about 1/30 of the nationwide generation. If you multiply our results by 30 to account for the total generation nationwide, the $175 million of production costs will add up to about $5.3 billion. And 90 million tons, the 3 million ton carbon reduction will add up to about 90 million tons, which is more than enough to offset all new automobiles sold in the US in a year. So that says something. And then there's about 1.5 billion in local benefits. And there's probably a huge amount of local short-term jobs and long-term jobs. Obviously, the investment cost is $2.7 billion for the first year only, and you'll probably recoup that in 6 or 7 months. The ongoing cost would be about $300 million. And excuse me, there. So in any case, it is.
Call from South Arlington. Call from South Arlington.
I apologize for that spam phone call. That happens always at the wrong timing. But finally, we're at slide 13. This slide shows the number of installments that we applied. Again, we did it on an iterative process where we had no GETS versus a case where we found what lines would bind and how we can apply the different GETS technologies. We start with dynamic line rating, and that's why you see there were roughly 56 dynamic lines that we applied dynamic line ratings to. A good chunk of that was 161 kVs and 138 kVs. We also applied 8 different installments of advanced power flow control on 8 locations. Again, the number of control is a lot less than dynamic line rating just because of the order of the analysis that we did. The software solution, we for unique topology optimization reconfigurations, which averages about 13 per snapshot. 13 may sound a lot to you today on a daily basis face thousands, somewhere in the 2,000 to 4,000 range of topology outages and other needs. So it's a very, very small fraction of what the operators are looking at. The estimated cost for all this is $90 million. One other way to think about it is if you think the new renewables are all getting the benefits, the 2,700 megawatts, $90 million divided by 2,700 megawatts is only about $30 per kW. The onshore wind investment is about $1,500 per kW. And I've heard from a lot of people will gladly cough up another additional $30 per kW, which is only about a real small 2% change in their initial investment cost if they can move forward with their project. So you see how small cost is compared to the benefits that's associated with these technologies. Now, the presentation that Jay and I have here, but I just wanted to show you the table of contents of the whole report. Talks about the different types of gets. It gives you a little bit of a background of each of the technologies, including dynamic line rating, advanced power flow control, topology optimization, and why they're relevant here. Section 2 discusses the study scope and analysis approach, which I roughly covered right now, but in more details, and how we did the analysis. Section 3 summarizes the results. It's very, very similar to what we but in further details. And the appendix includes a lot of detailed assumptions and the data that was used. So let me pause here and see if we have any questions. Charlie?
Okay, thank you, Bruce. We've got a lot of questions. We've got a lot of time left, so I think I'll just start picking from the Slido because I've been looking through the Slido as you were talking. In fact, you caught me looking through the Slido as you wrapped up. so Brian, you want to put the Slido up, or maybe I'll just go pull it up myself. Okay. The first question has it's been at the top from the very beginning. Grid enhancing technologies are often stopgap measures until a new line can be built. Is this temporary benefit worth the cybersecurity risk they can create? Did you take any look at cybersecurity in this study? Have any thoughts on that?
We did not. But I'd like to talk about that. And I think there's an educational effort we need to make sure people understand that all of these grid enhancing technologies are NERC SIP ready, and the operational reliability and resiliency benefits that these deployments provide all outweigh any cybersecurity risk, in my opinion. That doesn't mention the ratepayer savings and other economic or environmental benefits that you would realize as a result of deploying these technologies in the near term. In addition, I think these technologies can also help out in the long term. I do agree that we were looking at this in the next 5 years because there are some major transmission projects that are expected to be in service in SPP that'll help the congested areas we studied in 2026 and beyond. But these technologies provide benefits not only of the current system where there may be a lot of curtailments, but also in the long term. If we really want to get the most out of these big assets that cost hundreds of millions of dollars, it may make sense to spend a little bit more money and deploy grid enhancing technologies on the underlying system that exists today that will be the constraint for the outage of the new line that's being planned or proposed. I think that's all really important. Also, I think these technologies provide benefits in terms of measurements and calculations that are redundant with the EMSs today. And I think that can actually help cybersecurity, since you would get additional validation from these sensors and these devices that would help validate EMS data and calculations. I'd love to get Bruce's perspective on this question.
Yes, I agree. And there's been a lot of discussions about how these technologies can actually make you aware of the situation of the grid, because they're providing you with more information than what you have today. So trade-off, but as Jay said, they are NERC compliance. So we're not discounting the threat, but we don't think it's a showstopper.
Okay, thanks for that. Here's one that's been creeping up steadily, Jay and Bruce. Potential increases by DLR are widely touted. However, decreases in line ratings are ignored. Has anyone evaluated impacts of DLR on lines designed for 50 degrees C?
Well, we
I'll
didn't
start.
specifically
ahead,
look
Bruce.
at 50 degrees C, but we did find lines where the ratings did through the exercise when we applied the DLR ratings to it. And for those guys, we did apply the lower ratings of the lines, DLR findings.
So I think that's a great question, and it's a fact that static ratings today may actually overstate the capacity of the lines, a few percent of the time during especially the hot summer period where you got a high pressure system and you'd have no cooling on the lines from wind. But that's a risk that we take today. It's built into the static line rating calculations that are assumed for winter or summer normal and or emergency ratings, as well as seasonal ratings. But we specifically did not get into 50 degrees C line. We're aware of lines that were designed originally for lower than maybe 100 degrees C, like current lines. But the dynamic line rating should help the operators and the owners of the assets understand exactly what the capability of that line is based on real weather conditions, as well as, forecasted maybe a few hours out or next day. If you're wanting to get clearance for a line outage, you could actually use information to make better decisions based on real data to get accurate capabilities. I think that's really important going forward.
Okay, thanks for that. Here's a fairly straightforward one. How can the study be translated to regulated markets like the Carolinas?
Well, one thing is that we did not focus on any of the RTO specific metrics. So if you're an RTO, you may want to look into, let's say, the benefits against FTRs or whatnots. But all we did in terms of product and benefits is we looked at the carbon reduction and we looked at the production cost. These two metrics were chosen so that it's not RTO specific, but it can be applied to any system, whether it's under a vertically integrated utility, a municipal, or a fully unbundled wholesale market structured RTO type of market. So I think we can apply the sequence of the assets and the study with locational differences to any region. The structure should be pretty much the same.
Okay, thanks. Here's an interesting one. Could you explain about the sequence of the assets in your study, i.e. DLR, then topology optimization, then power flow control? Is it better from an operational or economic viewpoint? There must have been some method to your madness.
Yeah. So the first thing is DLR is the easiest to identify because you know which lines get congested when adding assets to a power flow case. So we said, okay, let's start with DLR. It's the easiest, it's the lowest hanging fruit, and it's the easiest for people to. Topology optimization gets a little bit more complex because you're changing the topology. But just for the audience, what we used for analyzing it was the topology optimization software, because it will help you identify where loads are, where it's close to the overloading, and therefore we use that software to identify the locations for DLR, use it to identify solutions for topology optimization, and then we went to the advanced power flow of thinking about what would be the easiest approach for analyzing it, given the time constraint that we had, the huge footprint that we had to deal with. So there was no economics behind it. It was more of the ease of analysis.
Okay, thanks, Bruce. Well, on the data, how did you obtain the data for the transmission grid? That's always a good question these days.
But can I start with that, Bruce, and you supplement if that's okay? We partnered, yeah, we partnered with Southwest Power Pool staff, and they agreed to give us the actual operating models after Bruce did his analysis to create the bins and figure out how we can get a balanced set of models across the seasons, across the days, to be representative of what we wanted to simulate and use to extrapolate for this analysis. So SPP staff was intimately involved in this on the front end. So we got the actual operating models that we used as a baseline. Then we worked with them to get the IDEVs for all of the transmission projects that were approved in the planning process. That's reliability upgrades, as well as economic planning projects, as well as sponsored upgrades. And one of the projects that actually is in the mix, and they're actually identified in the appendix of the report, of all the transmission projects that were added to the operational models to get to at least the topology. We did the same thing on the resource mix, right? We had to look at the planned additions to the fleet, as well as the retirements that are actually forecasted to happen in the next few years. And we pulled those into the models, as well as, like Bruce mentioned, we adjusted for the loads because of, I mean, obviously there's going to be a little bit of growth between now and then in 2025. And we know that Lubbock Power and Light's going to move from SPS in the Texas Panhandle over to ERCOT in the next few years. So we pulled that load out of the system. But SPP worked with us and help us get the models and help us validate the models, as well as the conclusions of the detailed results. There is a non-public version of the report that was shared with SPP staff that includes all the details on all the lines that were used for DLR, as well as the topology optimization configurations that were assumed, as well as the advanced power flow control devices and locations and amounts. So we wanted to make sure that the results were reasonable. And so we gave them the data. We have not shared that data with anybody else for obvious reasons, because it is a simulation and we wanted to make sure we're looking at the aggregate results and making sure they were representative. From my personal perspective, you know, I expected to see benefits from this. I did not expect the benefits to be as large as they were shown in these simulations. And that's even despite rather conservative assumptions in the modeling and in the approach to deploy each of these technologies. So I hope that answers the question. Bruce, you might have something to add about the data.
No, I think that's a pretty good summary.
Yeah. Yeah, good answer there, Jay. Next is a comment, which maybe leads to a question. The comment is that SPP starts curtailing at about 70% wind, I guess that's instantaneous wind production, to assure grid stability. This isn't a congestion problem. It's a low load issue and the need to maintain inertia. So I guess the question that comment leads to is, did you look at any other issues which might have driven the curtailment that you saw, other than just congestion?
Well, no, we didn't look at
Bruce, do you want to
whether,
handle it?
yeah, sure. We didn't look at whether it exceeded 70% or not, but we did assume a minimum generation for all the generators that were in the power flow case. And we did not touch nuclear units. We left the import exports as it is. I can't say with certain, but I'm pretty sure that we did not approach that 70% wind level, although maybe during certain snapshots we may have. But that we did not look into
Yeah,
to that. Yep.
Yeah, we that's beyond the scope of this analysis. We were looking at reliability assessments and power flow solutions, looking at thermal and voltage issues, and trying to maintain compliance with the existing planning criteria. So we didn't get into stability limits and things like that and inertia. Those are valid concerns and something we may need to look at some point. The congestion that SPP sees, I mean, they see it a lot, and Bruce pulled up that February slide of actual curtailments. You're going to see a lot of it this weekend, and I don't know if it's all related to thermal unit commitments that are required for stability at all. But we ought to investigate that and make sure we're comfortable with additional renewables on the system before we have other issues. I mean, there are weak grid issues and things like that need to be addressed, and we need to validate that.
Okay, fair enough. Thanks, Jay. A quick one here. Were any grid enhancing technology companies involved in the preparation of the final report?
The final report and analysis was done completely by Brattle. We did ask the grid enhancing technology companies for some support of the analysis. For example, the cost assumptions came from these guys. We also utilized their know-how about how much benefits or reduction in the line ratings would happen given the weather conditions. I think I said this, or I may not have. For DLR, because we knew the exact exact timing of the snapshots, we moved south and south to east wind conditions and took the minimum of those two to come up with the potential impact of DLR along with the temperature. And that analysis was done by the DLR vendors, but they did not know which lines we were applying it to and so on and so forth. So yes, they were part of the study, but they did not have the ability to say, hey, I want to increase this line by X or Y.
Okay, fair enough. This next question, I think, is a very interesting one, kind of a perverse effect, if you will. Do you have estimates of reductions or postponements in transmission expansion capacity, considering a massive introduction of grid enhancing technologies? Any thoughts there?
Yeah, let me start. Yeah, I don't have an estimate, but to be clear, we aren't looking at grid enhancing technologies to displace or defer or avoid transmission expansion projects that make sense and that are needed to support the clean grid of the future. Okay, we kind of see this as a stopgap measure to help get more out of the current system until we start adding more capacity and capability. We're not looking to use grid enhancing technologies to stop all transmission expansion. Okay, we do think that there's applications, especially as you start to replace old aging infrastructure and start taking long extended outages of major transmission lines that were built in the 50s and 60s, and you got to start getting 3-month outage here on this 100-mile 230 kV line, that it would make a lot of sense to deploy grid enhancing technologies in anticipation of that on what might be considered major constraints to the power system. I think that's going to be a bigger and bigger issue as we get to the point where we have to start taking big outages on big assets and creating topologies that may not be studied very well in the planning horizon, but could be real challenges for operations and markets in the near term, in the next few months, for example. But we gotta have more transparency about what outages are being requested. Are there ways to mitigate them? And I think grid enhancing technologies can help with that. The other point I'd like to make is, as we do start to add major backbone projects, there's going to be underlying constraints that pop up for maintenance outages and things like that. So, because the system, the resource mix is going to shift, everything's going to shift with every change to the grid. And we got to keep ahead of that and find ways to use technologies that are safe and secure and easily deployable and relatively cheap to get better information to make smarter decisions in the short-term planning horizons. I don't see grid enhancing technologies as a way to displace long-term planning expansion projects at all.
Okay,
And I'll augment that. One of the reasons that we chose 2025 is 2025 is a timeline that's not enough to build new transmission, but we can get away with gets. The grid enhancing technologies are portable, so you can install them, let them work until a new transmission line comes in, and then move it elsewhere. In another way of thinking about it, transmission lines are like roads. You need new roads, but in the meantime, when you don't have the new roads, a GPS system in your car will really help you operate your car or drive from point A to point B very efficiently. So the grid enhancing technology is like your GPS that you can bring into your car, your truck, or even your bicycle if you want to. It's portable, and once the new highway is done and you don't need it, you don't have to use it.
You can put it somewhere else,
thank you.
right, Bruce?
Yes.
I'm going to trouble with my screen here, but let me, a regulatory question here. I think I've heard this question asked many times. Do the study findings call for regulatory reform? Current regulations reward shareholders for spending capital, not for saving. What's your view on that?
That is the biggest
interesting
problem
question.
right now that we're facing. Sorry, go,
Yeah.
Jay.
That's a real challenge. Yeah, that's a real challenge. And, the business model for utilities are to spend money, make money, and understand that. And regulators want oversight of that and make sure that these are smart investments and provide value to customers. I do think I'm hopeful that based on the first announcement from last Thursday, where they're going to have a technical workshop on shared savings for grid enhancing technologies on September 10th, that will get the dialogue going and get some facts on the table and maybe some proposals on how to move forward with the benefits, not just going to the renewable developer or going to a local customer, but maybe even to the transmission owner who would actually be involved in deploying these technologies onto their system, or the ISO RTO also. I mean, there are risks to deploying these technologies. I think they're very manageable, but there may be some need to compensate TOs for doing something that they traditionally would not have done as a solution to a problem they've seen on their system over the years.
Okay.
And I would say that the Australian model or the UK model that has the shared incentives may be a good model for looking into and see what happens. Additional models may be going back to year 2000 when there were for-profit RTOs where they had some mechanism for sharing the cost of congestion. So there's different models that we can consider going forward. And as Jay said, there's going to be a FERC workshop in September to start that discussion.
Okay. Next question, one on O&M. We haven't talked much about O&M, but the comment is that the O&M cost of the gets is $10 million a year, pretty large fraction of the upfront capital cost of $90 million a year. Can you say something about the O&M requirements of the gets?
Yeah, so the 90 million and 10 million are approximate numbers. For example, the topology optimization software, you can license the software or you can use it as a service. And the others are the same too. You can acquire it or you can lease it. And that's why the 90 and 10 always have that approximate number in front of them, because there's multiple ways of implementing them. So I think that's certainly movable. If you think in terms of investment, yes, 10 million may be high, but if you think you're just licensing a software, then that's another way of avoiding that investment. So there's multiple ways of implementing these technologies, and that's why we came up with those numbers. It's not exact science, and it's also installment dependent.
Okay. We're getting to the top of the hour, folks, so we've still got a lot of questions, about 18 questions left, but I think that they can be answered fairly readily and sent out to the participants. So we're going to wrap it up, and I want to thank Jay and Bruce for the really helpful presentation. I hope everyone got something out of it. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get the answers posted as soon as we can. We appreciate your engagement and look forward to seeing you again soon at one of the 3 webinars we'll be conducting in May, something for everyone there. We hope you'll be able to join us once again for one of these events. And further information on all of our webinars and meetings can be found on our website at www.esig.energy under events and in our newsletters and informational emails, and you're all invited to attend. So Jay, Bruce, thank you once again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon.